a series of videos that provides a detailed and comprehensive explanation of Einstein's special theory of relativity. Episode 2. Einstein begins his explanation of the empirical physical foundations of the special theory of relativity. This episode will take us from Euclid through Descartes, space, time, the laws of motion, the law of inertia, the Galilean System of Coordinates, and examples of Einstein's famous Gedankenexperiments. We first provide a very brief introduction to the content of episode 2. We also offer some words of warning. First, the words of warning. Following the content of these videos, and thus Einstein's train of thought, will require some effort. Einstein made no pretense of having withheld from the reader difficulties which are inherent to the subject. The work he wrote presumes a fair amount of patience and force of will on the part of the audience to his book and our videos. On the other hand, he said, I have purposely treated the empirical physical foundations of the theory in a step-motherly fashion so that readers unfamiliar with physics may not feel like the wanderer who was unable to see the forest for the trees. The other warning concerns the quite low level of detail and step-by-step painstaking approach that is adopted to explain the contents of episode 2. You may well occasionally feel like the Times correspondent and ask something like, this is all very well, but what has all this to do with the theory of relativity? How does describing Cartesian coordinates and the law of inertia lead to the equivalence of mass and energy, E equals mc squared, time dilation, the behavior of measuring rods and clocks in motion, Minkowski's four-dimensional space? The short answer is that all these subjects have everything to do with the theory of special relativity. And the reason why Einstein carefully explains these subjects brings us to our introduction. At the end of the 19th century and beginning of the 20th century, many scientific advances had been made since the 1687 publication of Newton's Principia, but the theories of some distinct branches of physics were not coming together, and great doubt was emerging. The existence of the luminiferous ether had been strongly postulated as a medium through which light waves could be propagated. But the famous Michelson-Morley experiment, first performed in Potsdam, Germany, 1881, to detect the ether, produced a null result and had cast significant doubt on the existence of the ether. The null result led to much speculation and theories, including those of Professor Lorentz, who wondered whether rigid bodies in motion might undergo some sort of transformation, which might explain the null result. He was to pursue this problem in great detail. The results of the professor's studies will be covered later in this series. After the ether null result, it was even speculated that the trouble must lie in the new James Clerk-Maxwell equations of electrodynamics, which were only 20 years old at the time. With this state of uncertainty, Einstein took it upon himself to closely examine the very foundations of classical mechanics, to consolidate the loose strands of various branches of physics that prevailed prior to his 1905 submission of the theory of relativity. The introduction and words of warning completed, we are now ready to begin the journey through the empirical physical foundations of the theory of relativity in a step-motherly fashion. Einstein begins his book by examining the role of geometry in the science of mechanics. He not only decides on the appropriate role for geometry, but also describes a fundamental principle that will be used throughout his explanation of the special theory. The physical meaning of geometrical propositions. In his very first sentence, he praises the magnificent structure and the noble building of Euclid's geometry. He states that geometry sets out from certain conceptions, such as point and straight line, and from certain simple propositions, that is, axioms and postulates. Examples would be this point in absolute space, and a straight line such as the one joining these 2 points or places together, which aligns with Euclid's postulate 1. A straight line segment can be drawn joining any 2 points, and when a body travels from one point to another, the shortest way between the 2 points is a straight line, which is the geometric postulate first put forward by Archimedes of Syracuse. After thousands of years of the practice of geometry, we normally accept such statements as being true. But Einstein poses a crucial question when he says, if someone were to ask you, what do you mean that these propositions are true? For example, what do we mean when we say that it is true that a straight line can be drawn between 2 points in space? What do we mean when we say it is true that the shortest distance between 2 points in space is the straight line connecting them? Einstein replies to his own question. It has long been known, he says, that the question is not only unanswerable by the methods of geometry, but it is in itself entirely without meaning. Why is this? It is because, as previously stated, geometry is based upon axioms and postulates. The question of truth of the individual geometrical propositions is thus reduced to one of the truth of the very axioms or postulates upon which the mathematics of geometry rests. Geometry is not concerned with the relation of the ideas involved in it to objects of experience, but only with the logical connection of these ideas among themselves. We cannot therefore ask of geometry itself whether it is true that only one straight line goes through 2 points, when the straight line and 2 points are experienced in physical space, and we cannot ask of geometry to prove that the shortest distance between 2 points in space is the straight line connecting them. Isaac Newton neatly summarizes when, in the preface to the Principia, he stated that to describe or to define right lines and circles are problems, but not geometrical problems. Instead, the solution to these problems is required from mechanics. However, Einstein proposes a way of employing geometry in the science of mechanics, and it is this proposal that forms the fundamental principle involved in his explanation of the special theory that we referenced earlier. He says that if we supplement the propositions of Euclidean geometry by the single proposition that 2 points on a practically rigid body always correspond to the same distance, independently of any change in position to which we may subject the body, then the propositions of Euclidean geometry resolve themselves into propositions on the possible relative position of practically rigid bodies, and that geometry, which has been supplemented in this way, is then to be treated as a branch of physics. It is difficult to overstate the importance of this proposal, which is something that will become clearer as we progress. But for now, for a better understanding, we need to explain further just what is meant by a practically rigid body and the properties of such a body. A practically rigid body, such as this example, does not expand. It does not contract. It does not warp or deform and turn into the coupled concept of measurement. 2 points on a practically rigid body always correspond to the same distance, independently of any change in position to which we may subject the body, such as a train pulling the body along. No matter what velocity the train travels, the measurement stays unchanged. We offer a slight apology for this seemingly crude example of a train pulling a rigid body along a railway embankment, but you will see its relevance in just a few minutes. First, we summarize Einstein's explanation so far. Pure geometry as a branch of mathematics cannot be used to describe, define locations or lines in space. That is the job of mechanics. However, mechanics can use geometry to describe, define locations or lines in space if the locations and lines involve the relative position of practically rigid bodies. Geometry, which has been supplemented in this way, is then to be treated as a branch of physics. A very brief pause to let you know and perhaps reassure you that this opening of Einstein's explanation of the special theory in some ways is quite possibly the most abstract and philosophical section of the book. Going forward, the details get more physical and down to earth, with specific examples and Gedankenexperiments. Einstein goes into more practical physical detail when discussing the system of coordinates and how to exactly specify locations and times of events and bodies. He emphasizes the principle that every description of the scene of an event or the position of an object in space is based on the specification of the point on a rigid body, also known as the body of reference, with which that event or object coincides. He points out that this applies not only to scientific description, but also to everyday life. He gives an example. If I analyze the place specification Potsdamer Platz, Berlin, he says, I arrive at the following result. The Earth is the rigid body to which the specification of place refers. Potsdamer Platz, Berlin is a well-defined point to which a name has been assigned and with which the event or body coincides in space. This diagram shows the well-defined point Potsdamer Platz, Berlin on a map. But Einstein points out that this is just a two-dimensional view. It deals only with places on the surface of rigid bodies. We need a system that specifies the 3 dimensions of space. To accommodate this, he imagines a cloud hovering over the Platz. Like so. Then we can determine the cloud's position relative to the surface of the Earth by erecting a pole perpendicularly on the Platz so that it reaches the cloud. Like so. With the height of the pole, we now have 3 dimensions of our description. For precision, however, in the exact description of the cloud's position, we need a system of numerical measures. And in the physics of measurement, this is attained by the application of the Cartesian system of coordinates. The Cartesian coordinate system, being named after René Descartes, the French philosopher, scientist and mathematician. Einstein goes on to describe this system in more detail. The Cartesian system consists of three plane surfaces perpendicular to each other, such as the three surfaces shown here. Each surface forms an axis traditionally labelled x, y and z. The three axes intersect at the point called the origin. Einstein emphatically adds that the three plane surfaces must be rigidly attached to a rigid body. As an example of a rigid body to which the surfaces are attached, we select a railway embankment. This is a relevant example as Einstein uses it often throughout his book. He continues, refer to a system of coordinates. The scene of any event will be determined by the specification of the lengths of the three perpendiculars or coordinates x, y, z, which can be dropped from the scene of the event to those three plane surfaces. To demonstrate these instructions, we show three plane surfaces rigidly attached to the rigid railway embankment. An event takes place. To specify the exact location, we follow the instructions of Einstein. We drop perpendiculars from the scene of the event to the three plane surfaces. And in terms of numerical measurement, we note the lengths of the three perpendiculars or coordinates x, y and z. In this example, the coordinate values chosen are arbitrary and used for illustration only, but could be, say, x equals 6, y equals 5 and z equals 3. The unit of measurement can be of our choosing. It could be feet, meters, yards, miles, kilometers. Whatever is appropriate can be selected. The description of the scene of the event can thus be recorded as x equals 6, y equals 5 and z equals 3. Einstein has thus instructed us how to define a location or static event in space. In his next topic, space and time, in classical mechanics, he analyzes more complex and dynamic examples of events and the motions of bodies. He states that the very purpose of mechanics is to describe how bodies change their position in space with time. He first examines the concept of space and states that it is not clear what is to be understood by position and space. To show the lack of preciseness in the term space, he conducts a Gedankenexperiment. It consists of a stone, a pedestrian, a train, a carriage, and a train embankment. Einstein imagines that he is standing at the window of a railway carriage which is travelling uniformly, and without throwing it, he gently drops a stone onto the embankment. Then, he says, disregarding the influence of the air resistance, I see the stone descend in a straight line. But Einstein then asks us to consider the relative experience of a pedestrian standing on the embankment footpath who is observing the approaching train. The pedestrian sees the train approaching and sees Einstein drop the stone out of the window. But the stone does not fall in a straight line relative to the pedestrian. Instead, the pedestrian notices that the stone falls to earth in a parabolic curve. Einstein asks of us, do the positions traversed by the stone lie in reality on a straight line or on a parabola? In answer, it is possible that many people would shrug their shoulders and say something like, both points of view are correct. But Einstein is about to adopt a much more consequential and strict stance. He asks what is meant by motion in space, and answers with the statement that in colloquial terms says, in fact, we have not got a clue what space is. His actual words were that he entirely shuns the vague word space, of which we must honestly acknowledge we cannot form the slightest conception. We should replace it with motion relative to a practically rigid body of reference. And if instead of body of reference we insert system of coordinates, which is a useful idea for mathematical description, we are in a position to say the stone traverses a straight line relative to a system of coordinates rigidly attached to the carriage. But relative to a system of coordinates rigidly attached to the ground or embankment, it describes a parabola. With the aid of this example, he says, it is clearly seen that there is no such thing as an independently existing trajectory, but only a trajectory relative to a particular body of reference or system of coordinates. Having given that perspective on space, Einstein moves to the subject of time. He states that in order to have a complete description of the motion, we must specify how the body alters its position with time. That is, for every point on the trajectory, it must be stated at what time the body is situated there. So if we selected the motion of the stone, as seen by the pedestrian, for example, it must be stated at what time the stone is situated there. How do we do that? Einstein says that if we take our stand on the ground of classical mechanics, we imagine two clocks of identical construction. The man at the railway carriage window is holding one of them and the man on the footpath the other. Each of the observers determines the position on his own reference body occupied by the stone at each tick of the clock he is holding in his hand. Again, using the example of the pedestrian, a time value corresponding to each click of his clock is therefore assigned to the relevant position of the stone along its trajectory. Adopting those instructions, if we refer to the earlier example of how to define an event or body in space, we need to add the element of time, the coordinate for which is usually assigned to t. The earlier illustrative example thus gains the time coordinate t, for which we add an arbitrary value, say t equals 1 second. So the full coordinate values of the event becomes x equals 6, y equals 5, z equals 3, and t equals 1. Before finishing the explanation of space and time, we need to briefly mention one thing regarding the two clocks and Einstein's stipulation that they are of identical construction, and thus they record identical durations of time, no matter where their location. Now, in everyday life, we are quite used to times being synchronized globally, so that a duration of 1 hour and 2 minutes is exactly the same duration whether the timing devices are located in, for example, Berlin or New York. But although we are quite accustomed to this, we still need to record the assumption of classical mechanics that if two clocks are of identical construction but located in different reference bodies, nevertheless the clocks will record identical durations. This assumption will play an important part in the Gedankenexperiments that Einstein will conduct throughout his explanation of the special theory of relativity. That for now brings us to the end of Einstein's explanation of space and time in classical mechanics. He will have much more to say on these matters later. We now move to the next step in Einstein's train of thought and the last section of this video episode. Einstein introduces the law of inertia and the Galilean system of coordinates. This is a very short section in his book, but a very important one. He is describing another set of conditions that apply to the special theory of relativity and to the Gedankenexperiments that he will undertake. This refers to the type of reference bodies or system of coordinates permissible in mechanics, and to uniform motion. First, what is uniform motion? In episode 1 we noted that special relativity relates to all systems moving with uniform motion, that is, moving in a straight line with equal velocity. The forthcoming Gedankenexperiments in this series will feature a train moving in a straight line with equal velocity, and its reference body or system of coordinates will be inertial or Galilean. What does that mean? The law of inertia was first asserted by Galileo. The law is with respect to horizontal motion on Earth. It states that a body in motion would remain in motion unless a force caused it to come to rest. Later, it was expressed by Newton as the first law of motion. Every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Einstein introduces the law in this manner. He states that the fundamental law of the mechanics of Galileo Newton, which is known as the law of inertia, can be stated thus: a body removed sufficiently far from other bodies continues in a state of rest or uniform motion in a straight line. He now makes crucial points. This law not only says something about the motion of bodies, but it also indicates the reference bodies or systems of coordinates permissible in mechanics and which can be used in mechanical description. A system of coordinates of which the state of motion is such that the law of inertia holds relative to it is called a Galilean system of coordinates. To summarize, special relativity itself and its explanation is not only constrained to systems moving in a straight line with equal velocity, but this uniform motion must be relative to a system of coordinates called the Galilean System of Coordinates. Such systems are referred to as inertial frames. With that, we come to the end of this episode. Episode 3 will introduce the principle of relativity and the theorem of the addition of velocities employed in classical mechanics. If you enjoyed this video, you are invited to join our community on locals.com. This link will take you directly to our site.